And now we're going to talk about essentially computational substrates. Um, how do FPGAs compare to other devices, which is related to programming model, but it's not just programming model. So what are they good at? What are they bad at? Okay, so I'm going to give you an overview of how we can compare different programmable devices. So processors and DSPs and GPUs and FPGAs, but from a very high level. So you can take entire courses on every single one of those things. So I'm not going to dive down into every detail of their architecture. Okay, let's start with the CPU. So CPU is always if it meets the need, probably a CPU has the easiest programming model to use, so it's probably what you should do. And there are a lot of different kinds of CPUs. What I'm showing here is a high-end CPU. Well, let's see if there's anything going on in the chat here. Okay, so the live stream is working. So a high-end CPU basically is doing work, whoops, see if I can do that again, is doing work here in the ALU, right? Your ALUs were actually doing computation. Everything else is just kind of moving data around and figuring out what to do. So in a high-end CPU, you're fetching instructions from your caches or main memory. You're decoding them to figure out what they're telling you to do. And in order to get better performance, have more parallelism, high-end CPUs pretty much all now are out of order. And I think you probably most people know this, but everybody know what an order-of-order processor is? You know these terms? Okay. So then somebody should be able to define it. What do I mean when I say it's an out-of-order processor? Yeah.
Instructions will execute, like if some instructions are waiting on data dependencies, like read after writes, but other instructions are not, then they can dispatch those instructions to functional units before the earlier ones do, and then they'll correct them so you can reorder faster after.
Yes, that's a very good answer. So basically, they don't follow the instruction order in your program. They follow the data dependencies. So they're fetching some window of instructions. They're looking through that window of instructions, figuring out which instructions have all of their data ready and hence can launch. And because some of those, they're doing things like predicting branches. Okay, branches make that harder to do. You have an if statement. You don't know which instruction is going to execute next, so they predict that. So they build a fancy branch predictor, spend a bunch of hardware guessing which way a branch is going to go so they can keep fetching from the right spot, keep executing instructions from the proper window, because they might guess wrong. They do another part of what Isidore said. They have some speculative state, like they have some answers that they're not quite sure should actually be written back to the register file or main memory, because maybe they mispredicted the branch. So they use something called a few techniques, but one of them is a reorder buffer to make sure that everything that goes back into what the end user sees, even with a debugger, is for sure correct, right? Even though they've been executing instructions out of order based on their prediction of where branches are going to go and what's ready to do. They also have a problem with waiting for memory, okay? So this out-of-order engine is basically just looking for things to do, and it can easily wind up with nothing to do if it's waiting for data to come back from memory. Typically takes now hundreds of clock cycles to make an access to main memory from a high-end CPU. So you have a memory prefetcher that's trying to guess what memory addresses you might need and bring those from main memory into the caches in advance. All these red things, like, they don't really do useful work. They're to figure out what to do next, keep track of all your state, etc. So they make your programs run faster, but from an efficiency point of view, they're kind of all overhead, right? So what else do we have? We have some centralized storage. Okay, so this slide comes from Mike Houston, who formerly of AMD, now at NVIDIA. The execution context is basically your register file that's storing the data you're working with, okay? And not everything's going to fit in the register file, so you have a data cache, which also allows you to kind of decouple from main memory. So the prefetcher is guessing what you might need next, bring it into the data cache, all to keep this kind of Ferrari engine going. So this is like a big, power-hungry engine. The goal of the high-end CPU is being to maximize single-thread performance. Okay, so you got one program running, one serial thread running, make it go as fast as possible by figuring out the next instructions to run figuring out where the branches are going, make sure the data is on chip, etc. And the high-end CPUs are really good at that. They now want a bit more than that. So you can only, the gains from making all of these things more complicated are diminishing. Okay, so you can make your out-of-order control logic more complicated. Look at a bigger instruction window. Try to launch more instructions that are ready in one cycle. That's called your issue width. You can make your branch predictors more fancy. So throw more logic at them, throw more state. But all of these things cost more area, and they get some returns, but diminishing returns. So that means even high-end cores are not getting that much better at single-thread performance. They're getting a little better as we go to new process nodes and have bigger transistor budgets, but not a lot. So they do other things that will convince you to buy their chip. And those other things are, well, can we get a little more throughput, right? So aside from just doing really well on single-thread performance where we're making decisions, the classic thing that processors are good at, if we have more parallelism in our program, could we make use of that? And what they do is, first they use a certain amount of SIMD. All high-end processors now have single instruction, multiple data instructions. Okay, so the classic instructions say, add register 1 to register 2, just works on scalars. But they also have instructions that say, add all 4 numbers in this bigger, vector register to the 4 numbers in this other bigger vector register. So that would be 4-way SIMD. And the SIMD has been gradually getting wider. So some high-end processors have up to 16-way SIMD, where you might do 16 numbers at once with, add 16 numbers at once with a single instruction. Yeah?
Just to clarify, just maybe obvious areas in the room, but just to ask to clarify. In order to make sure that this SIMD isn't just pure overhead, is this just dispatching the same instruction to multiple functional units at the same time?
Yes, it's one instruction that controls multiple function units.
But those functional units each individually could have been controlled by other out-of-order instructions.
Not usually. So usually, in theory, you could do that. You could say, let's build 16 functional units and have one instruction controlling those, but also you could take 16 scalar instructions. I don't know of any processor that does that. Okay. When it's not used as overhead, yeah. If you don't use those SIMD instructions, those extra functional units are not used. The reason that's done is nowadays, these out-of-order logic, et cetera, is bigger than your functional units. So that's what I mean by, there's this ALU, and now we don't have just one ALU. If I can launch multiple instructions in a single cycle, and if some of those instructions might actually say, let's do 4 or 16 additions, then I really have more than one ALU. But the ALUs are actually smaller than all this other stuff. Does that make sense? So most of your area, most of your energy is actually going into just keeping this stuff going, okay? The other thing that happens is, or has happened, is we can make multiple cores. And a core is really what once would have been called a processor. We don't know how to make, if we have 10 times the transistor budget and we throw it all at this out-of-order control logic and branch predictors, make them super complicated. First, it's very hard to design, so it's a difficult processor to make correct. But we're not going to get anywhere near 10 times the performance, right? You might get, I don't know, maybe you get 50% more, maybe you get 2x. So you get diminishing returns. So with the huge transistor budgets we have now, almost all high-end processors also include multiple cores. And the terminology that the industry is largely settled on is they call a chip still a processor, and a core is what we once would have called a processor. It's like a standalone CPU. So we can have 4 of those in your laptop probably, maybe your desktop, and in high-end servers, this can be 64. So for AMD and Intel, which make most of the high-end chips, their top-of-the-line servers top out at around 64. And you probably can't buy even a laptop processor with less than about 4. Does that make sense? Yeah.
Here's a good question. Would you put superscalar under the ALU or under the out-of-order control logic?
Superscalar I'd put under out of order. So does everybody know what superscalar means? Does anybody not know what superscalar means and they're willing to tell me? Okay, so superscalar means that you can issue more than one instruction per cycle. Okay, so a classic processor, you issue one instruction at a time. Superscalar says, no, I have many functional units, so I don't just really have one ALU, I have a whole bunch of these things. And if I find 2 or 4 instructions that could all issue, if I made a 4-way superscalar processor, all 4 of those could issue in one cycle. Does that make sense? And most, well, high-end CPUs are both out of order and superscalar nowadays. It varies, but it would be fairly common to say it could launch 4 instructions in one cycle if it could find 4 instructions ready to go. The processor is deeply pipelined, so usually it's about 12 or 14 pipeline stages. So if I'm trying to, if I manage to launch on average 3 instructions per cycle, and I've got a pipeline depth of 14, I've got around 40 instructions that I'm working on all the time, and this out of order logic is keeping track of a lot of stuff, of like which of these instructions do I know for sure I predicted correctly that they should be run, which ones are wrong, which operands are ready for the next set, and so on. There's a lot of logic here. Okay, so has everybody got it? But they work well. I mean, our processors have gotten a lot faster. And multiple cores have changed programming a lot. If you go back 15 years ago, people didn't care very much about, most people didn't write parallel programs. But then as every processor started including multiple cores, it became much more important to try to write parallel programs to use that. Okay, so that's a high-end CPU. So what's a graphics processor look like from 1,000 feet or 10,000 feet? So, I mean, it's a processor. There's a reason it has the word processor in it. So it's still got an instruction stream. It's still got functional units and a data path that we reuse. So it is a form of processor. But it makes different design decisions. First, it has a lot of ALUs. So I only showed 1 ALU in the previous slide. Here I'm showing 8. Okay, so in reality, you know, there's really more ALUs than that in the processor and even more in the GPU. But basically, a GPU spends more area on functional units. And it spends less area on figure out what to do next. Okay, so it does have to fetch instructions. It does have to decode them. It does not have fancy branch predictors, out of order execution, etc. It's going to execute the instructions in the order that the program presents them, and is not going to try to figure out what to do next. So if the program has to be written so that you can tell what to do next with a lot of speculation. So its control is much simpler. And part of making its instructions more efficient is it's built for SIMD. So you saw that CPUs are now, they have both conventional instructions that are called scalar instructions, and they have SIMD. The GPU is really built for SIMD. 8-way or more. And they started out with about 8-way, and now they've gone to a larger amounts of SIMD, where one instruction controls many operations. And the reason is exactly what we talked about in our programming, our compute models. We're amortizing that instruction fetch. We're going to bring in an instruction, we're going to decode it, but we want it to control a bunch of operations. The CPU, high-end CPUs focus on keeping a single thread going very fast. Okay, so they're trying to guess what the branches are doing, figure out what to do next. A GPU doesn't worry about that. The GPU says, I have a lot of work to do that is independent. So they're originally written for graphics, and it turns out that the pixels on a screen, most of the calculations they need to do for the pixel here are different than the calculations, well, they use different data than the calculations for the pixel over here, but you can use the same instructions. So GPUs were written that way. Repeat these instructions over a whole bunch of pixels, each of which is being blended in the same way, but using different input data. So that's why GPUs evolved to have this SIMD architecture. But it turns out it's useful for other things too. Okay, so they are highly multi-threaded. They have caches. So a processor spends a lot of area on caches to try to keep memory that you've accessed recently nearby, data that you've accessed recently nearby. A GPU also has caches, but most of them are programmer managed, okay? So, which is often called a scratch pad RAM. So it physically is almost the same thing. It's just that the programmer has to say, put this data in this memory. The hardware doesn't figure out to do it automatically. That gives the programmer more control, and it simplifies the hardware. And this is how they tolerate latency, is basically if you have enough threads, when you need to get something from main memory, you just switch to another thread, okay? So they're just going through a whole bunch of different threads that are doing independent computations so that they can just do a little bit of work on one thread, switch to the next one, the next one, the next one in like a round robin fashion, And by the time they get back to thread 1, the data's come back from main memory. So they don't have to worry about caches as much. So they're fundamentally built for throughput. They're not built for latency. They're built to get a lot of work done when it's independent, whereas high-end CPUs have predominantly been built to, I've got a single-threaded application, it should go really fast. Does that make sense? I guess then in context is your register file is the most obvious context. Instead of having one register file, like kind of one context, they have a lot. A lot of context means basically every thread can have its own storage, and I'm just switching between different threads that are each using different contexts in kind of this round-robin way so that I can tolerate the fact that it takes a long time for data to come back from main memory. I'll just have a lot of threads that I'm switching between in a very simple way to kind of cover that memory latency. Make sense? Okay. So there is some convergence. I've kind of shown you like the kind of classic where are these two architectures coming from. But everybody steals ideas from each other. That's actually good engineering, right? So if it's patented, you should probably go pay a licensing fee. But if you don't look at what your competition and other people are doing, that's actually not smart, right? So you should go look at what other people are doing. So CPUs are adding more cores, more function units, and more threads. So I guess the classic CPU was, one core. When I just already told you this, we've gone to more like 4 to 64 cores nowadays. CPUs, if we go back about 25 years, they didn't tend to have any SIMD. And then I'm following kind of the x86 path. Similar things happened for other processor families, but it went from no SIMD to something called MMX, or multimedia extensions. So that just did integers. You could do integer calculations with SIMD. And this was done a little bit cheaply. They took kind of big functional units and like multipliers and chopped them into smaller ones. So it was kind of closer to what you were saying, Isidore, where they didn't want to spend too much area on it. So it was limited amounts of SIMD, and it was for kind of small operands. Then they started doing it for floating point, because floating point's important. And initially, an instruction set called SSE did 4-way SIMD for floating point. Then they made another instruction set. These are basically all new instructions that are gradually getting added. So they made one called AVX, and then AVX2. And AVX2 did 8 times single precision. And then they did one called AVX 512, which is initially used in a processor called Xeon Phi that was intended to compete with things like GPUs and supercomputers. But it's now in a lot of Intel and AMD processors. And it does 16-way SIMD on 32-bit floating point values. So the SIMD's gradually gotten wider. Most of the processors that you would buy, going into desktops, laptop servers nowadays are between 8 and 16-way SIMD, because AMD and Intel, this is kind of where they are right now, right? Half of the processors are 8-way, half of them are 16-way. If you narrow your operand, so basically to do, let's say AVX 512. AVX 512 actually does start to get expensive. When your SIMD gets wide enough, you have enough functional units and your registers are big enough, your data paths are wide enough, it does actually start to hurt, okay? So now the functional unit areas are significant. But this is a 512-bit wide data path, right? 16 times 32, that's how they got the number. If you use narrower operands, so for machine learning, there are 16-bit floating point numbers that are actually quite useful for machine learning. Usually that's enough precision to train a machine learning model. And for this narrower operand, AVX 512 can do 32-way SIMD, because the 512-bit data path is wide enough, the registers have enough bits to handle that. So that's another common thing you'll see in processor SIMD. They have a small ability to switch threads. So they have something that Intel calls hyperthreading. The academic term is simultaneous multithreading. What this is even with all that complicated out-of-order logic, once you have 4 or 6 different functional units in your processor, which is what a modern high-end processor usually has, and you can issue 4 instructions in a cycle, it gets actually hard to find 4 instructions that are ready most clock cycles. When you're just looking at one thread, right, like a single serial program. So what most processor vendors have done is they basically say, well, we'll let the processor run 2 threads at once. And it basically is that instruction window where it's looking to see what can I do next is actually looking at both threads. Just the instructions for those 2 threads are interleaved in there. Some of them it's grabbed some instructions from one thread, some instructions from the other. They're tagged with which thread they came from, so it knows what they came from. And it's just looking which ones are ready to go. And that allows it to use more of its function units more times. Doesn't scale very well. Okay, if you went to 4-way simultaneous multi-threading, you don't get much more, right? Your functional units are now kind of busy, so you add more hardware and don't get much. But it turns out 2-way works pretty well. On the machines we have in the UG lab, on the programs, well, one of the programs that I wrote for an undergrad course, you get about 50% more throughput by using 2 threads. So it's not 2x the throughput, but it's about 50% more throughput. And the cost of adding this extra hardware is not that high, okay? Does that make sense? So it's able to grab instructions from 2 threads. So this has changed things some, but still there's a heavy focus on single thread performance. That's a key workload for high-end CPUs. They still throw a lot of hardware at all of that out of order and branch prediction and so on. Yeah?
So when comparing to the GPUs, GPUs have, I mean, in addition to a large number of actual cores, each of those cores are running a large number of threads as well.
Yes, GPUs have like a lot of threads, okay? And they switch between them generally in like a round-robin fashion. This is kind of, I have 2 threads going on a core, and I'm not really switching between them. I wrote switch in 1 cycle, but I should probably change that. The dominant way hyperthreading is done is that you're actually grabbing instructions from both at the same time and sending them to the function units. GPUs are more going through a very large number of threads in like a round-robin fashion. There's no what's ready, et cetera. It's just, it's your turn, right? You go, and then it might be another 128 cycles before you go again. Does that make sense? Yeah. And I'll fill all that other 127 cycles with 127 different threads. So there's no guessing who's ready. I have 128 cycles to go get whatever I need from main memory and be ready again. Does that make sense? Yeah. Okay, the clocks are reasonably high, so 3 gigahertz, maybe a bit more. And I'm going to tell you the details of the UG machines because you're going to get assignment 2 soon, probably right after Thanksgiving, but not before, so you can enjoy your Thanksgiving. And one of the things I'm asking you to do is you're going to do a comparison between a convolution. So you're going to do a convolution, which is a key part of signal processing and also deep learning. And you're going to do it on a CPU, but we basically give you the code, so the CPU part's pretty easy. A GPU and an FPGA. And the FPGA is the one we want you to focus on optimizing. The other 2 we're basically going to give you the code. We want you to compare the efficiency and comment on it. So you need to know, well, what CPU are you running on? In the UG machines, it's an Intel processor. This is its name. It has 8 cores. It's manufactured in 14 nanometer process technology. And that's important because we're going to compare. We don't actually care about who's got the better process. We're trying to see who's got the more efficient paradigm. Its clock frequency varies. So power is such a constraint for everything nowadays that a CPU has power throttling circuitry. So it'll run up to 4.9 gigahertz. But if you actually use those AVX 512 instructions all the time, it actually generates so much heat, it'll drop back down to more like 2.5. And it's basically got some dynamic temperature control to do that. So you can't actually say it's 1 frequency. You'll probably be closer down to this 2.5. And it has AVX 512, so it can do 16 floating point numbers in parallel. And it dissipates about 65 watts. Okay, so that was CPU. Now let's take a look at a little more detail in GPU. And again, the example I'm using here is the one in the UG machines. So it's a pretty recent GPU, and you want to know what's in it so you can compare to it. So it's an NVIDIA GPU. This is its product code. It's the Ampere architecture, which is a recent basically all these processors, they have part codes that don't mean that much. What really means something is what's called their microarchitecture. So this is NVIDIA's Ampere microarchitecture, which I think is 1 behind their latest. So pretty recent architecture of their GPUs. It's actually a more advanced process technology than the CPU. It's 8 nanometers, and it's in certain UG machines. NVIDIA is like taking it's interesting. NVIDIA prices their chips kind of the way the FPGA companies do. They go, the market is strong, we make up the prices, okay? So therefore, the NVIDIA GPUs are only in certain UG machines. What's inside this? So what I'm showing here is a diagram of what NVIDIA calls a streaming multiprocessor. And a streaming multiprocessor is essentially what a CPU would call a core, okay? It's like a complete processor. They're going to put a whole bunch of these on one chip. So they have 48 streaming multiprocessors. Each of them has basically almost 128-way SIMD, okay? So for 16-bit floating point numbers, because they can actually do 16-bit floating point with a wider degree of SIMD, they can actually do 128 of those per cycle in each one of these streaming multiprocessors. If you get into the details of how they do this, it's not quite 128-way SIMD. They basically have 4 32-way SIMD units. It's basically a little bit more flexible. Those 4 units don't have to be doing exactly the same thing. So it's close to 128-way SIMD because they're not fully independent, but it's a little bit more flexible. So I guess if you were to put it in processor notation, it's kind of like you can issue 4 instructions, each of which is 32-way SIMD. So it's not exactly that, but it's close to a 4-way superscalar SIMD processor. It's also reasonably close to a 128-way SIMD core, but as I said, it's a little more flexible than that. Let's see. It has large register files and some on-chip shared memory, and those are explicitly managed. Okay, so explicitly managed means they're like scratchpad RAMs. You decide, put this here, put that there, rather than the hardware deciding where to put it. Like a cache just says, if you use this data recently, I think I should keep it in the cache until I decide I shouldn't. The register files in a GPU are managed by the programmer, and the shared memory also can be managed by the programmer. So I guess I told you that CPUs are adapting. They're getting more SIMD, a little bit more threads, more cores. GPUs are also adapting, but they're adapting kind of in the opposite direction. So early GPUs, basically all of the on-chip memory was managed by the programmer. So it'd be called register files or scratchpad RAMs. You decide what to put in there. In recent GPUs like this, you can also ask for some of that memory to be essentially turned into a cache, where it's hardware managed. Hardware managed means the hardware just decides something was used recently, I'll keep it there. So it has an L1 data cache of 192 kilobytes per streaming multiprocessor. But you can also choose to manage some of this explicitly. So it basically has given you the option now of I'm finding it so hard to program this. I'm just going to say hardware, take care of it. I'm not going to do it. It has a level 2 cache that is always hardware managed. Okay, a 4 megabyte one per chip. So that's shared by all 48 of these streaming multiprocessors. The clock is a bit lower, so 1.5 to 1.7 gigahertz. So their clocks can also vary based on heat dissipation, but not usually as much as CPUs. And their clock frequency is not low, but not quite as high as a CPU. And the power is high. So the power budget for this chip is 290 watts, so significantly above the CPU that we have down there. The last thing that's in here are these tensor cores. So tensor cores are basically small matrix multiply units. They're like do little 4x4. They can multiply a 4x4 matrix by another 4x4 matrix, and there are a whole bunch of them in here. So so why are these here? In linear algebra and deep learning, it turns out you do a lot of matrix multiply, and you can build up big matrix multiplies as the combination of a lot of small matrix multiplies. So that's important enough that recent NVIDIA GPUs have these tensor cores to make matrix multiply more efficient. Does that make sense? So what I'm showing you here is like one of the 48. Any questions on any of this? Yeah.
You know how you said in GPUs, it's like a round robin fashion thing, right?
Yeah.
Is that within each core or is that across the cores?
That's within each core. So that's a good question. So this is maybe hard to see unless you're on Zoom. So this is maybe an example where Zoom is better. These are like FP32, okay? And there are 16 of them here. Not shown is these can be divided into two FP16, so you'd get 32-way SIMD. And then there are 4 of these. That's how we get to the 128. Okay, so that's maybe where the SIMD is coming from. This is maybe hard to read, but it says register file. And it's basically over 16,000 registers that are 32 bits each. That's, for a processor, that would be an enormous register file. And it has 4 of those, okay, for a core. So this the reason it has such a huge register file is that's where the round robin's coming from, okay? And it's built right into the NVIDIA. This is a part of NVIDIA's cleverness, right? It's built into their CUDA programming flow that you basically talk about threads, and they're mapping what the data for each thread to different registers. That's what allows them to say, I'm going to have a huge number of threads running, and each of them is getting its data from a different register and putting its data back in a different register. And I have so many of them that even though I'm taking maybe accessing 32 registers a cycle, because I have 32-way SIMD here, that's still like 512. I can do that for 512 distinct locations. That's a lot. That actually allows me to kind of walk through a bunch of data in my register file and be writing to a bunch more data that's far away, so that I can essentially have these threads kind of going in round robin and gradually walking, like say I'm adding 2 vectors. I might start by adding register 0 to register 1 and do that across 32 registers. So maybe register 0 to register 33, right? And then I add register 64 to register, it's hard to do this in binary, to like register 95. And write those into different registers way down near the bottom. I have enough registers that I can actually do that a lot of times before I have to go get my partial outputs and do something with them. Does that make sense? And so that's how they schedule their instructions. And then their instructions are SIMD. So one instruction is controlling all 32 of these. So that's another source of efficiency. So it's built for SIMD with, essentially I got a lot of threads and I can tolerate a high latency to main memory. Does that make sense? Okay. Okay, so that's GPUs and CPUs. There's a third major class of processor called digital signal processor that you probably haven't worked with as much. Who's ever used a digital signal processor? So a couple of you have. Okay, but they're widely used, but not as much. They're used in signal processing. So they're a major market, but they're not as obvious as CPUs or GPUs. You don't see them in people's laptops as much. So they're optimized for signal processing. They tend to have simpler control, just like a GPU. They focus on repetitive loop processing. They typically have lower power targets. This is just kind of what they target. GPUs, you saw that was 290 watts. You're not going to find, I don't think, any DSPs that have that much power budget, because usually a DSP is going in sort of more embedded devices. And nobody wants to get like, I don't know, a remote control that has got some voice features, or a speaker that you can stick on your desk that like dissipates 290 watts, right? Because like the remote control is like, setting fire to your couch and stuff like that. So they, just by the virtue of what they go into, they tend to have lower performance, but also much lower power budgets. They're optimized for multiply accumulate. That's kind of the key operation in signal processing. And there are a wide variety of DSPs. Sometimes they have separate data and program memory. I'll just show you one DSP architecture. This is a high-end DSP architecture from TI, and it's referred to in one of the papers that we're going to talk about today. It's a VLIW architecture, so it's got multiple functional units, and the instruction controls each of them independently, so that's VLIW. This particular one has 4 address units, okay, so they're specialized to go get me data from memory, 2 general ALUs, 2 multiply accumulate units, And the multiply accumulate units, depending on the chip, they can do a little bit of SIMD, so they could do two 16-bit operations, or some of the later versions can do, they widened the SIMD, okay? So instead of two 16 by 16 multiplies, they could do 8 16 by 16 multiplies or 4 floating point. Digital signal processors, some of them have floating point, but a lot of them are actually integer because they're, again, targeted at power efficient processing. If you can spend the extra effort to do it in fixed point or integer, it does save you power. A lot of DSP processors just don't build the floating point units, right? They say you were looking at efficiency, you should be doing it fixed point, but there are some that do have floating point, and this one does. Let's see, another thing they do is, remember I said centralized storage is a bottleneck? So they have a register file, which is what a processor kind of needs, a register file, and it's part of what makes the processor easy to program. But to make this more efficient, this chip partitions the register file, okay? So they basically divide it into two pieces. Half the registers they call register file A, half they call register file B. It's a VLIW architecture, so there's multiple function units. So load, store units, multiply, accumulate, etc. They connect half the function units to these registers, half the function units to the other registers, and then they have one connection between them. So you can have a move instruction that takes data from one register file and puts it in the other. So basically the compiler knows this. It tries to keep data that these functional units are using in this part of the register file, keep data that the right functional units are using in the B register file. It has the ability to move between them with an instruction, but it wouldn't get good performance if you were kind of randomly accessing them. This kind of shows how big a deal central storage is. It's basically making big register files with many ports, like letting lots of functional units talk to them, is expensive. This is one of their techniques to try to minimize that while not making the device too hard to program. Let's see. So much like a GPU, they can manage the memory yourself. Yeah?
When we talk about DSP cores, we don't mean files, right? Like Ethernet file, USB, that's separate.
You don't mean, sorry, what did you say?
Files, like an Ethernet IP.
No, so these DSP processors are, they are processors. They're intended to do, but they target at signal processing applications. So this would be one of the competitors actually to FPGAs I mentioned cell phone base stations. So I told you that there's a lot of signal processing on the other end of your cell phone. And this is now a few generations ago. One of the big competitors to FPGAs there was DSPs. FPGAs actually became enough more efficient because of their spatial processing model that for the most repetitive parts of signal processing, a lot of the filtering and modulation, they eventually sort of ejected DSPs. So early in my career at Altera, like what you'd hear from the sales force, they're competing against this TI DSP and so on, and eventually they just won them all, okay? Because the processing demands got high enough in a cell phone base station that at least the parts right by the antennas, where there's really high data rates, FPGAs took over completely. As you got into some of the slower processing that was more complicated, that was sort of deeper in the base station, then we still compete with DSPs. I don't know if that was entirely relevant to your question or not, but it is still about processing, multiply, accumulate, doing a lot of filtering, a lot of modulation, that kind of stuff. Does that make sense? Yeah.
More of a sillier question, I guess. How do DSP processors relate to DSP blocks and FPGAs? There's just no connection.
I guess the connection is that FPGAs were initially used for logic, right? Not really for multiply accumulate. They weren't optimized for it. They didn't have hardened multipliers. They had, so you could build multipliers because you can build anything out of logic elements. But because you're making it out of something that's much more programmable, it was more expensive. Xilinx was the first company to put hardened multipliers in an FPGA, and it was smart. They were basically going, hey, if we did this, we could actually be very efficient, more efficient at a lot of signal processing, for example, that's going to be a big market. Then Altera said, well, we're not just putting multipliers in, we're going to put multiply accumulate with a little more programmability, and we'll call it a DSP block. And the reason to call it a DSP block is it sounds like this, right? This is the market you want. They're doing multiply accumulate. They're called digital signal processors. We'll have a digital signal processing block, which tells you you should use this instead of that. So that's actually a very logical name, but it really comes down, that's it. That's where it comes down to. This is what we think it should be used for, so that's what we'll call it. So it could have been called like multiply accumulate block, but that probably wasn't as cool. So, okay, so yeah, so this particular DSP, you can manage the memory yourself, and that's often done because these are also used sometimes in applications where you really want real-time response. Like you want to guarantee that I'm going to process this at this rate, not 99% of the time, but all the time. If you need that guarantee, explicitly managing the memory yourself can make you more predictable. This particular design chip has, 32 kilobit L1 caches and 256, or kilobyte L1 caches, 256 L2. And TI makes a whole bunch of variations on this. So some that do only fixed point, some that do floating point as well. What I showed you was essentially one core, one processor. You can buy more expensive chips from TI that have up to 8 of these cores. And they'll actually combine them with some hardwired, basically like streaming accelerators. So they know these are going into signal processing communication applications a lot of times. So they'll put in hardwire. Some of the chips you could buy from TI have no accelerators. Some will have FFT. Some will have Viterbi decoders, etc. So they are, ASICs that are like suited to their purpose. And they also make something called OMAP. And the reason I'm telling you some of this is you'll see it in the paper that we're talking about in a few minutes. OMAP mixes an ARM processor plus one of these DSPs. Now the DSP is a processor, so you could do anything on it, but it's really optimized for multiply accumulate. So to make it easier to do control processing, they just stick an ARM processor in it if you need also a lot of control processing. And these target relatively modest power budgets. There's a wide range. For this particular family of DSPs, it goes from about 1 watt to 20 watts. And as you go to these versions that have floating points at 8 cores, you'd be more up at 20. If you go to a low-end one, you'll be more down at 1. TI has other DSPs that go all the way down to like 100 milliwatts, right? So, but I'm not going to tell you about their architecture. They basically, they're the same idea, but they just strip everything down. Lower performance, but very low power budgets. Okay, so let me summarize that. So DSPs, CPUs, GPUs, they're all forms of processors. That's why they all have a P in them. Their power budgets vary a lot. High-end CPU is usually around 100 watts. A GPU is high-end GPU is more like 300. DSP, there's not much market, or maybe no market up at that range, so they're more like less than 1 watt to maybe 20. FPGAs are a pretty broad range. So low-end FPGAs are less than 20 watts, often a lot less. Like really low-end FPGAs are less than 1 watt, so they span a very wide range. You can even get ones that are down in the 100 milliwatts, et cetera range. But the high-end used to be, 8 years ago, the high-end was around 20 watts. Like you didn't get many designs above that. But as FPGAs have gotten bigger and we're not getting as much power reduction from process technology, the high-end is now more like 100 watts. Still less than a GPU, but in the same ballpark as a high-end CPU. There's some convergence between these things. So GPUs and DSP processors have gotten a little easier to program. So putting in caches, putting in floating point, and they sacrifice a bit of performance for that. Everybody's leveraging SIMD. Okay, so DSPs leverage a little. High-end processors are leveraging it quite a bit now, and GPUs the most of all. Whoops. But there's some divergence, right? So a CPU still spends more area on single thread performance. GPUs are all about getting throughput. So when you've got a lot of work to do that's independent, so it's all about tolerating latency through many threads. And DSPs are, a bit different still, right? They rely on the programmer to schedule things more. They have less kind of the hardware adaptability than a high-end CPU, and that makes them more efficient for things like multiply, accumulate. And they're not as focused on, give me tons of power and I'll do tons of things at once. They have more limited number of things to do it efficiently. Okay, FPGAs kind of rely even more on the programmer. So this, you really design everything. So you can create a custom and highly distributed memory system. You can create your own custom memory pipeline. They're the best at small data types. because this doesn't take as much hardware to build that. So these other devices, they get some gain from small data types because often they can do more SIMD. So the SIMD gets wider. You know, instead of 16-way, they might be able to do 32-way if you use a smaller data type. But FPGAs are kind of unique of, you can make the data type even 1 bit smaller and the hardware will get somewhat more efficient. So they kind of adapt to the data type in a more granular way. They historically have been weaker at floating point, but that's changed in the last few years. So ARIA 10 is an Altera chip. It was the first FPGA that put in hardened floating point. So you could do floating points in FPGAs, but you basically had a lot of shifters to try to line up the mantisas, the integer part, and that was pretty expensive. It's a whole bunch of muxing and a whole bunch of logic. So ARIA 10 put in hardened floating point in the DSP blocks. And there's a paper on this, if you're interested. It shows they did it in a fairly clever way that kept the cost pretty low. When that was first done, it wasn't clear it was a good idea. It was controversial. So I was in Altera when that was being kicked around. And you know, you can always do things at lower power and lower area if you do them in fixed point. So there was an argument of, well, FPGAs are for people who know what they're doing. They should do it in fixed points. It'll be better. You don't need floating point. But it's harder sometimes to figure out how to do it in fixed point. So this went in. Wasn't clear if people would use it enough or not. I think now it's clear that it was a good idea because later Intel FPGAs have all kept the floating point units and now Xilinx has put them in too. And once once the kind of main FPGAs sort of agree on something, it usually never comes back out, right? When one company does it, there's a chance that it's a mistake and the next generation it comes back out again. Once their competition does it too, it means it's probably never going away. Yeah, and FPGAs, again, they're not actually a processor. So you can build a processor in them, but they don't need an instruction stream. So they are quite different. They can directly do streaming. Yeah, that's true. Yes, so it fails my test of if there's a P, it means processor. I didn't think of that. Okay, how many people read this paper? Well, actually, before I do that, any questions on this? So this is a very fast overview of, you could take entire courses now. I think we have like several courses that cover CPU and GPU architecture. So if you go, wait a sec, he didn't dive into that much detail, you were totally right, okay? But any questions on any of that? I think it is important to have a high-level understanding of how these things fit together so you can kind of decide where you might pick one or the other. Yeah?
A very good question. Do you know what the program model is for these DSP processors?
Yeah, that's a good question. So typically C, okay? So C or assembly. Those are the two different ways.
So when you do the memory management, it's done by the program. Is it actually done by the compiler then?
Yeah, that's a good question. Okay, so typically, I mean, when you have a script, they often do double buffering, okay? So they'll have like, you have a memory with explicit addresses, so that is on chip, okay? So you can basically do loads, and you load to this address, and you know this range of addresses is actually my scratchpad memory. So you can still do that in C. You don't have to write in assembly. Some DSPs, so let's take TI, they're the #1 DSP processor maker. They have some DSPs that their instruction set is very complex, okay? So it's very CISC. Like you have a single instruction that means multiply these two numbers, add them to an accumulator, increment the loop counter, and increment your address counter and get the next memory, okay? So you can pretty much write a loop with like 1 or 2 instructions that would be doing, let's do a convolution. You know, let's multiply this set of coefficients times this set of data, and you could do it with a very small number of instructions. That's not the one that I showed you, but some of their other 5000 series DSPs, that's what their instruction sets look like. It's efficient, right? Like the instructions say, do these loop, multiply, accumulate options that you want in signal processing, but it's very difficult for a compiler to do it. So a compiler will do it, but doesn't get the most out of it. So to get the most out of those, people write assembly code. A lot of that assembly code is written by TI, so they have like pre-packaged functions for things like FIR filters and FFTs that are quite efficient. But I think, you know, there's pressure even when you can make some of those subroutines, it gets hard to keep that all up to date. So the 6000 series, right, which is one number bigger than the 5000 series, was targeted at higher performance, higher power budget, and be an easier compiler target. Because part of what you get with higher performance is you usually get more functional units and so on, and it starts getting harder for people to write this assembly language by hand. So this is a VLIW architecture. It can be, efficient code can be generated by a compiler. You know, probably you could still beat it hand-tuned. But like the previous generation, which never went away, because if you actually want really low power budgets, that previous generation is what you should use. Basically focused more on you're going to write assembly code. So I guess the two dominant ways, C or assembly. And it's been gradually moving more to C, and the architecture has been actually changing to make that easier. Does that make sense? Okay, so let's go through the first reading and we'll take a break. So how many people read this paper? Okay, a few. Other people are like, no, I think there's going to be more later. That's fine. Okay, so this, any thoughts? For somebody who's read this, what did you think? Do you have any, like, something you liked, something you didn't like? Let me make that maybe more, you can pick one or the other. If you go, I only disliked things, then that's fine. Just give me one thing. So, is this one? Yeah, Vespa's the other one. This one is basically doing like peak metrics. So, anybody read this paper? Or is it just me? Okay, so what did you think? Something you liked, something you didn't like?
So it has a lot of ethics that is included in this paper, and basically I think the chart they compare between different types of devices. So some are making sense, but some I do not think it is sufficient for their conclusion.
Okay, so you thought there was some validity, but you think some of their conclusions might be a bit too strong. Is that correct?
I think that they do not include all the specs there. I mean, they have some assumptions, but the assumptions are not totally reasonable for some cases because, like the power, I mean, for the toggle rate, they just assume the toggle rate will be the worst case, it will be 100. But
This is a great insight, actually. I totally agree. So, yeah. Okay, so I'm going to come back to you as we get to that. So you found some value to it, but you think some of their assumptions are not the most reasonable. And one of the things you're worried about is how they calculated power, which is a very good point because I actually don't like the way they calculated power either. So, and one of my metrics of like a really good comment is if it agrees what I think, like that's, you know, it's a simple heuristic, but I'm going to go with it. So yes, so let's dive into it then. But I'm going to come back to you because I think those are good insights. Okay, so this paper is trying to compare a whole wide range of devices. So GPUs, CPUs, FPGAs, DSPs. So that's a lot. And it's going to be hard to take a whole bunch, like one way to compare those is take a whole bunch of applications, optimize for every single device, and try to get trends across different kinds of applications, different kinds of devices. And that would be a great study, but it's extremely hard to do because you're going to see with that Intel paper that you may read next week, it actually takes a lot of effort to fully optimize for a certain platform. So what they do is they say, okay, we're not going to do that. We know this isn't as accurate, but we're just going to compute peak metrics that we think are relevant and could help you decide which of these platforms is a good one maybe to explore, maybe a couple of platforms. And that peak metrics are dangerous, okay? So because a lot of devices never get close to their peak performance. On the other hand, you know, it's guaranteed you won't exceed them. So maybe there's some value to them too. And that's the way I take all the things we're going to talk about now. Like they're peak metrics, so don't take this as that's what I'm going to get, but they still, I think, have some value. So they divide these kind of peak performance metrics into a few things. So they talk about the compute density of a device. So the compute density is they want to say, well, how many operations could this thing compute per second under best case scenarios? And they want it to be a little more realistic than just let's count all the functional units and multiply by the clock frequency. So they say, well, to be useful, you got to have some memory system on chip that can feed these functional units at that rate. So they have to take the memory units on chip must be, what is the rate at which they can feed computational units? And the computational unit they select is a multiply accumulate unit, because that's a pretty important building block. And they'll be limited either by just how many multiply accumulates they can do or how fast they can feed data. And they're going to compute that. They're also going to do a normalized version of that where they say, let's take that amount of compute and divide it by the watts. So we get compute per energy, compute per joule basically. which is probably more important nowadays than just raw performance, right? Most computations in the end are power constrained. That's all on chip. You also have to get data in from off chip, so they compute how much bandwidth does each device have to external memory, and how much bandwidth does it have to essentially every other kind of I/O, which is PCI Express, serial transceivers for things like Ethernet, etc. So and they're going to compute these things. And has anybody heard of a roofline plot? Maybe not. A roofline plot is kind of like a guaranteed not to exceed performance, right? You will run out of computation if you're above this, or you'll run out of memory bandwidth if you're above it. So it's not saying you'll achieve that, but it is guaranteeing you will not exceed that. So that's essentially what they're doing. They're producing this multi-dimensional list of maximums. Okay, so how do they do this? So in an FPGA, they focus on, well, let's do integer ops. They actually do different kinds of operations. So they're going to see what the impact is of the operand type. In the FPGA, they build one multiply and one add unit. They measure how fast that's going to run, so they get the Fmax for it. Then they replicate it until the device is 85% full. So kind of like what you do for Lab 1, where you say, how many copies can you fit this in? They do it until it's 85% full because they reserve 15% of the logic for essentially control, steering, some muxing to get the data to the memories and so on. So they don't assume that they can fill it to 100%. They assume they can fill it with these data paths to 85. They make sure that the internal memory bandwidth can feed it. So in this particular case, they'll take 2 block RAMs and say 1 block RAM's feeding basically one of the operands to this multiply accumulate, the other block RAM's feeding the other one. And if you run you need 2 block RAMs for every one of these multiply accumulate units, because they're assuming that they each could be kind of doing independent things, so they each need their own independently addressable memory, 2 memories. So for example, in one of the architectures they look at, Vertex 6, they find they can build 968 multipliers, they can build 969 adders. So they'll say, okay, well, that means 968. That runs at 296 megahertz when they just have one of those in the device. They assume that that'll be the same as they fill it up. They have enough block RAM memory ports. So actually every block RAM in this device has 2 ports, so they can get 2 pieces of data out of it. So when they look at how many RAMs they have and the fact that each has 2 ports, they find they have 1,064, they can get 1,064 operand pairs, okay? So that means they're okay. They can get 2 items times 1064. So they're limited by this, the multiplier count. They multiply the number of multipliers by a frequency, and they get a total number of operations per second, so 287. Okay, what do you think? Do you like this methodology or don't like this methodology? Yeah.
I think this seems really, really optimistic. There's a few different reasons that come to mind for that. I think one that comes to mind is just that you can't just have these units in standalone. There needs to be logic to move things around. And then if you just say repeat until the device 85% full, you may end up with some Fmax limitations. You may end up with routing stress as you're facing these things, trying to route everything together. I don't see anything in here about getting data in and out of the chip.
Yeah. So that's all assumed to be sort of in their extra 15%. So yeah, I think it's a good point. 15% is probably optimistic for most things. It might be fine for some. Like if you actually were doing some big pipeline of data, probably fine. But for many other cases, 15% is kind of low. And as you fill a device up, in a lot of FPGAs, it gets harder to maintain the performance. And if you connect things in more complicated ways, you get additional timing paths. So I think you're right. There's some optimism here. Any other thoughts on this? It comes later. So I think it is optimistic. It's not, in my opinion, wildly optimistic, like 10x, but they might be optimistic by 30, 40%, because maybe this 15% was too low. Maybe they lose some clock frequency. There is a pessimism possibly here too. They're assuming that these multiply accumulates all have to get their data from block RAMs, and they don't necessarily have to, right? Often you can chain operators. That's actually a very powerful technique in FPGAs. getting everything from block RAMs is essentially like everybody's got a FIFO in front of them or a scratch pad memory. And sometimes you need that. But you saw in our compute models, if you can actually say, look, I just need regular registers, I don't need so many memories. So in this case, that wouldn't really help them with compute density because they didn't run out of memories anyway, although it would help them with their power calculation. Does it make sense? But yeah, and you can also see the fact that it's probably mostly optimistic, but in some cases a bit pessimistic. It's kind of the limits of a peak analysis, right? Like it can only convey so much information. Okay, so and they do the same kind of thing for processors. They look at if I use your best SIMD, I use all your cores, all your functional units are kind of fully utilized, everything's in the register file, or I actually can't remember if they use register file or L1 cache, but basically in the lowest level, like the level of the memory hierarchy that's closest to the processor, can I keep you fed? So they do a similarly kind of best case analysis for the various types of processor. And so what do they get? So these are all the processors. And I'm not going to go through all the details of this, but I guess a few interesting trends. These are like kind of the high-end CPUs. And you can see that these ones basically do a bit better on int16, and it's because they get more SIMD. Okay, so in this particular x86 CPUs, the SIMD width is wider if you're doing 16-bit integers than if you're doing 32-bit integers or floating point. They have Xeon Phi. Xeon Phi is a processor that is focused on very high core counts, okay, and wide SIMD. So Intel made it to go into supercomputers, basically. And it but basically focused a lot on floating point because of the fact that it was to go into supercomputers. So it gets pretty good performance on floating point. The DSPs have really low performance, those TI DSPs that I just showed you, which might look bad, but you have to wait till you see the power numbers. And then you have a bunch of GPUs. And this paper's a few years old, so these are older GPUs. But basically, you can see at that time, GPUs really focused on single precision floating point. So the red lines are very high for the GPUs. You didn't get a lot by going, or anything, by going to integer. And double precision floating point really cost you a lot. And it still does cost you a lot in GPUs. GPUs don't care very much about double precision floating point, whereas processors do. Processors get used a lot for scientific computing, GPUs not so much. And then these last ones are basically, again, DSPs, but they're the DSPs that just add in an ARM processor for control. Okay, so this is the same plot for FPGAs. The scale is not exactly the same number. This goes up to 6,000, this goes up to 3,000. So what can you grab from this? Well, FPGAs really like small operands. Okay, so it's like the first order thing in an FPGA. If you want to go to an FPGA, you want to try to use small operands. They do much better at 16-bit integer than at 32-bit or floating point. So every increase in precision costs in an FPGA. As we go from, Vertex 6 to Vertex 7, the numbers get significantly better. And Vertex 7 isn't much different than Vertex 6, except it's one process generation ahead. Stratix 4 versus Stratix 5 aren't very different, except there's one process generation. So process matters. You just get more parallelism. So maybe that's obvious, but it means you never want to do, you want to try to take that into consideration if you're ever comparing two compute substrates and there are different process technologies. You don't want, I see all sorts of papers where people just ignore that, right? So it's not possible generally to perfectly correct for it, but you don't want to ignore it. You want to acknowledge it and try to correct for it. And let's see. Okay, so that's peak performance, and maybe it's not super surprising. FPGAs like small data types, GPUs are very good at floating point, and general processors are kind of in between. If you look at compute density per watt, what they did in this paper is for the fixed function devices, like the processors and the GPUs and so on, they used the max thermal dissipation specification. So there's a certain maximum power that this device is guaranteed not to go beyond, and they use that. So what do you think of that? Is that fair? So for the GPU or CPU, they just take the number from the data sheet. And for the FPGA, they don't do that. They actually do a more complicated calculation. So any concerns about using that number? Yes, you're concerned. What do you think? Think it's going to be too low, too high? What? What's that?
Unless you're going crazy with like the
Yeah, so one concern could be like, well, it's penalizing them because it's beyond what you would actually get. Maybe I'm not doing so much work. What do you think, Isidore?
Another thing which just also comes to mind is depending on what the limiting factor ends up being. Like if you decide the limiting factor is, let's say, the amount of memory you can get in and out, or bandwidth, you know, then the power that it's actually distributing in the core is not going to be this peak power because it's not limited by the number of computations.
Yeah, yeah. So it would be better if they actually measured this, because you're right. So these are two reasons that they could wind up over-predicting power. I suspect that in the end here, they probably don't over-predict power. They might actually slightly under-predict it. The reason is this is the max thermal dissipation spec, but certainly these processors and GPUs actually have, they have on-chip temperature sensors, and they'll throttle the clock and drop the voltage as they start to heat up too much. And this is no longer like an academic, in theory this could happen. This happens all the time, okay? Like if you go measure what throughput you get on your GPU, you'll actually see it drop as it heats up. My group, we bought a couple of GPUs. Let's see, okay, this is recorded, but I don't think anybody from NVIDIA is gonna watch it. Okay, so I told you NVIDIA has like gotten really good at like price point selection. So they figured out that there are two markets for GPUs. There's people putting them in servers who are often doing machine learning. Sometimes they're serving up graphics to people at home, but either way, they're in a data center. And there's a consumer market doing gaming. And they have different tolerances for cost, and NVIDIA has more competition in the gaming market than in the data center and deep learning market. So what they've done is they have differential pricing. So I needed to buy a couple of GPUs to do deep learning training on. And to buy a GPU, we could buy a GPU for about $2,000, which is expensive, that had pretty good performance on machine learning training. We could buy one that had about 25%, 30% better performance that cost over $20,000. So you can go buy the $2,000 one. Except the $2,000 one has a cooling solution that will not go into a server. Okay, like it's built to be laid out for this will go in your desktop computer, but it's going to be completely misaligned with the system fans and the case. So I asked one of my grad students, what do you think? Could you MacGyver this? He said, I think I could do it. So we bought the $2,000 one, and he basically just drilled holes in the cooling solution, left the case half off, et cetera. It's a really bad cooling solution, and the chip throttles itself, so we can see it throttle to about 65% of its peak performance, which is still better than the server one on a dollar per calculation basis. But yeah, so it's not hypothetical at all. We can actually see the GPU slow down as you kind of use it for a little while. The server one also probably wouldn't run at its peak either, though, right? It's probably do better with a better cooling solution. But you hit these things all the time. That's why the processor also, like in the undergrad labs where it says it's 2.5 to 4.9 gigahertz, it's a huge range. And there's lots of articles you can find online. If you go use AVX 512 on all your cores, you're dropping down to like that 2.5 gigahertz. Like the clock frequency drops a lot. So my guess, it's hard to say. This is a challenge with peak memory, peak things, but probably because they're saying, let's take the peak frequency of this device and all the compute units are fully going and let's get the compute density for that. That's probably beyond the thermal dissipation spec and the device would throttle itself. So my guess is actually a little bit optimistic for the processors, but I can't prove it either, right? So what do they do with the FPGAs? So for the FPGAs, power is always a function of, it's always dynamic power plus static power. And in FPGAs, generally FPGA manufacturers don't give you like a peak power because it's so dependent on your design, you can do anything that is not meaningful to say this chip takes, 60 watts or 20 watts or something. So instead they have tools that let you calculate this. So the static power is pretty easy. You can get that from the device spec. It just varies with temperature. So you take the maximum temperature and get the device spec. Dynamic is basically charging and discharging capacitance. And if you go through the math of that, it's a half times the capacitance times the voltage squared times the frequency times the probability that you actually are switching. Okay, so if every node in your circuit, every single transistor, every gate, switched every cycle, that's the end. Okay, because everything's getting charged and discharged. Charged one cycle, discharged the next. That's the equation. But in general, circuits you don't have all your logic switch every cycle. Okay, so this alpha is what fraction of my logic is actually changing from a 1 to a 0 or a 0 to 1 every cycle. They assume the device is 85% full, because that's what they assume for the compute density. They use the maximum frequency reported by the CAD tool, and they use this alpha that's set to 100%. So what do you think about the FPGA one? Think this is realistic? You think it's optimistic, pessimistic? What do you think?
I think the alpha being set to 100% is ridiculous.
Yeah, the alphas actually is kind of crazy. I don't know why they did this, okay? This is actually one of the hardest. The rest of this is relatively easy for you to get from the CAD tools and your design reports. The alpha's hard, right? Generally, you have to use a simulator to get it. But 100% is not reasonable, okay? Because in a design that is where, if you just have random signal processing tends to actually have high activity. So you're doing a lot of multiply, accumulate. On average, you'll have a node switch half the time, okay? Like it might be a 1 cycle and then 0 the next, but it's basically random. There's no real correlation from one cycle to the next, but that still only switches it half the time. This is, what they're looking at here really is kind of signal processing, so 50% is probably reasonable. In most other designs, like a finite state machine, your control logic, muxing your data path, the activity is actually well under 50%. So for those ones, people often, it's not well justified, but people often assume 12 and a half. Like if you actually go to the vendor tools, you'll see generally the default is like 12 and a half. But there are designs where it's 50. 100 is bizarre, okay? So their power numbers for the FPGA are quite high. Yeah?
Just curiosity, do FPGAs throttle, is there any throttling provided by like the vendors that you can opt into for FPGAs?
It's a good question. They have temperature sensors on them. Depends on the FPGA, but the recent ones, they have to worry about power enough that they do have a temperature sensor as well. And you can hook into that in your logic and decide what to do. So you could implement throttling yourself, but they don't do it automatically because they don't know what does it mean if you throttle. If you go into some, say communication system, right? And you actually have designed it that this many packets come in, this many packets go out, and there's no back pressure, throttling you could be a big deal. Like you're just arbitrarily dropping packets. And they might prefer to raise an alarm, right, instead of doing that. And like somebody goes in with a fire extinguisher. I don't know exactly, like it's not a good situation, but it may not be so easy for them to just throttle it. In some systems, it might be reasonable. So they give you the hooks to do it, but they don't automatically do it for you. Does that make sense? And yeah, FPGAs usually are in more of a fixed performance environment. Where I need to make the following happen. It's a big deal if I don't. So I think the power numbers for an FPGA are optimistic. One thing that's relevant, so this is actually relevant to Lab 1, right? So part of the power differences you're going to get in some of the different compute styles, don't forget this alpha. Like what is it? So I told you that 100% is really high. There are cases where you can, and like 50% is just random. There are cases where you go above 50%, okay? So it can happen, but you as a designer can fix it. So I'll leave you with that thought. So if you want in the break, you come ask me about it. So yeah.
For the lab, the power that it's reporting when you use the test bench, that's using the actual toggle rates from the power analyzer.
Yeah. So the reason in the lab it shows you how to get these alphas accurately, right? If you run through a simulator, it will actually tell you, it actually records not just for one signal, but for every single signal, how much does it toggle. If you you put in a test bench that operates your design in its normal mode, then you're getting very accurate toggle rates, and you're not even getting like one average one. You're getting like a different one for every signal, and it's all getting added together. So that's good. If you ever find these toggle rates are really high, there are reasons that can happen, but you can fix them in your design. So ask me if you're confused by that statement. Okay, so let's go, maybe we'll finish this paper and then we'll take a break. Okay, so I guess I just gave you the methodology. This is the compute density per watt that they get for the processors. And like, what can you see here? Basically, the GPUs did pretty poorly on this. They did pretty well. They did okay for floating point, but they don't do very well for the smaller operands because these GPUs were optimized for floating point. The CPUs actually did okay, especially if you're using the smaller operands, like integers and so on. And the DSP processors, these are like these kind of mixed DSP processors with an ARM. They're actually really power efficient, okay? So they looked really terrible on performance because they were like the worst, but on power efficiency, they're very good. And that's largely just kind of what architectural choices did they make. So the scales are, again, different on the FPGA. So this goes to 100 gigaops per watt. When we go to an FPGA, it actually now goes a bit higher. It's going to 140. Basically, it shows there's a big power advantage to using smaller operands. So from 16-bit integer to 32-bit integer to floating point and then double precision floating point, we're taking large degradations in our power efficiency as we do that. It's roughly quadratic as we go from 16 to 32. The power is, basically this is a more advanced process node, Vertex 7 versus Vertex 6. And you can see the power efficiency is better in Vertex 7 than in Vertex 6. Okay, so it kind of made sense the performance would get better because we just can fit more stuff on the chip, so we get more parallelism. Does it make sense to you that the power also got better? So what do you think? If you've been waiting to answer a question, you go, it's like a 50-50 shot, so you just go for it. So what do you think?
I guess because since the process node is smaller, I think the interconnects are smaller, so maybe, there's less delay. You could probably, charging is less, so your capacitance go down, maybe power gets better.
Yeah, so that's a good answer. So if you remember that equation I showed you, it had 1/2, okay, so dynamic power was 1/2 CV squared, and then times frequency and times alpha. Okay, frequency and alpha, that also, like alpha's the same, no matter what process node. And if frequency goes up, well, processing goes up too, so that cancels out. Capacitance goes down, right? As you make everything smaller, your capacitance on your wires and your transistors get smaller. They get closer together, but they also get smaller. If you actually work that out, you'll see that the capacitance drops as you go to a smaller process node. The voltage also has historically dropped. That's been slowing down, but still the voltage usually drops a little bit as you go from one process node to another. It used to drop a lot, and that meant power was really good. Now it's a bit harder, but you still get a reduction in dynamic power, basically, as you go to the new process node. Now people get worried about static power. Yeah? Yeah, so it's a good question. So as you go to a smaller node, the transistor threshold, typically you try to scale the threshold voltage down, and your devices become less ideal. They have more variation because they're smaller, and that tends to increase your leakage. And there were a lot of scary plots that you probably have seen. Maybe some of you have seen this. Maybe these plots have now started to disappear, showing that static power is going to go to infinity, and the whole electronics industry is going to die, right, or stagnate. That didn't happen. Because if you just took the same, if you didn't worry about it, you didn't worry about static power at all, you just say, shrink all my transistors and it takes what it takes, then static power would have gone through the roof. No one can do that. So basically, whenever you shrink a device, something from one process node to the next, part of what you have to do nowadays is figure out how you're going to control leakage. So you might increase the threshold voltage, you might use power gating, you might use something called back bias. There are a lot of different techniques you can employ. All of them cost you some performance. You might drop the voltage. All cost some performance, but you have to do it. So you basically sacrifice some performance until your static power is reasonable. Reasonable generally means it's about the same as the previous generation, right? In the previous generation, if you could tolerate 20 watts of static power, you can still tolerate 20 watts of static power. And if your dynamic power is 60, 20 is not so bad, right? If you shrank this and your static power went from 20 to 100, that's not good, right? Because if your dynamic is 60, now static is too much. So basically, static power would get out of control if you didn't do anything. Nobody makes chips that way, okay? So they will sacrifice performance until it's under control. So we still do get power reductions as we go to the latest process nodes. Okay, so if we're to compare these things, the FPGA did very well on 16-bit integer ops. Did about 10 times the compute density per watt of a GPU, or about 5 times that of a CPU. It didn't do as well on floating point, right? So its strength is integer, smaller operations. Let's see. So the best results are, go to the most advanced process nodes. You still get gains from that. Floating point results, the FPGA gigaops per watt were about the same as the GPU, but the overall throughput was lower. Okay, so it wasn't actually a terrible result in efficiency, but it wasn't a clean win either. This paper predates when FPGAs got hard floating point. So right after the last chip that was shown in this, ARIA 10 came out, which increased the floating point bandwidth by putting floating point units in. And it had 1,700 of them. And then as you go into more recent chips still, you get even more. So the next generation after that basically increased the number of DSP blocks to over 5,000, and you got over 9 teraflops. If we compare it the same process node, so this is a 14 nanometer FPGA, if we compare it to a 14 nanometer GPU, they have around the same number of teraflops. GPUs build a lot of floating point units, but the FPGA typically was at a lower power. So I would say for floating point, GPUs are still extremely strong, but with hardened floating point, FPGAs now can compete on efficiency, at least in many cases. But it is one of the areas where GPUs are really strong. So if you're just doing a lot of floating point and storing the result back to memory, that's kind of what a GPU was built for. If you can chain the floating point operations together and do some more custom stuff, that favors an FPGA more. Okay, and I think we'll take a break now for 10 minutes, and we'll talk about the last little bit of this after that. Okay? So we'll get back at 5:45. Yeah.
I have a question about assignment 1.
Sure.
Yeah, for the shared operator part.
Yeah.
Are we supposed to define our logic
Okay, so let's talk, we're still doing this peak analysis. The other thing this paper looked at was I/O bandwidth. So these are the processors, and let's see, what can you see here? The GPUs have the highest bandwidth, okay? And they break the bandwidth into two pieces. They have, the lighter portion is the bandwidth to external memory. So in this case, you know, the GPUs were typically using graphics DDR. All graphics DDR is it's just conventional DDR chips, and they basically tighten up the specifications, right? They tighten up the specifications so you can communicate with them at a higher rate, and they're usually soldered right on the board so that you have less signal integrity issues, you just cycle them faster. There's not really a whole lot different. Other chips could choose to communicate with that kind of memory if they wanted. But you see that GPUs basically just choose to emphasize a very large amount of external memory bandwidth. And then the darker bar is everything else. PCI Express, Ethernet, et cetera. And GPUs don't put much into that. Processors put more into it. And then if you look at FPGAs, okay, and the scale here was like 700 gigabytes per second was the peak. FPGAs, the scale is a little lower, but not that much, 450 gigabytes per second. The main memory bandwidth is significantly below that of GPUs. So it's like 100 instead of, 500 or so for the highest end GPU. But it's kind of reversed. The solid line, which is your Ethernet, your PCI Express, et cetera, is much more. Why do you think that is? Do you think there's any fundamental reason for that? What do you think? Yeah.
I think it's the compute model. I mean, like when you look at GPUs and stuff, the compute model is you're going to talk to memory, read and write everything just going through memory. For FPGAs, you're streaming in data, could be coming off various different types of like Ethernet or other input.
Yeah, so that's a great answer. There's not a lot of technological reason that these have to be different. FPGAs could choose to have a whole pile of memory chips around them. But they basically are optimized for somewhat different applications and compute models. FPGAs are used a lot in communications where you care about bandwidth to Ethernet, somewhat bandwidth to PCI Express, and you do want main memory, but you don't need as much of it. There is probably a little bit of a technological difference here. Of the memory controllers in FPGAs tend to be more flexible. I talked about the PHY give you an example a week ago or so of how the PHY that talks to DDR and other memory chips in FPGAs is difficult to design. Part of what makes it difficult to design is that you want flexibility of this. FPGA can talk to all sorts of different memory standards in all sorts of different ways. There is a cost to that, right? The more general PHY doesn't run quite as fast. So there's a reason that GPUs will probably find it easier to drive memory bandwidth somewhat higher, but not anything like this. So most of this is just defined by what application they're going after. Okay, so yeah, GPUs have about 3x the bandwidth of memory of FPGAs. The latest GPUs and FPGAs can both talk to high bandwidth memory, which is basically a 3D stack of DRAM chips, usually 8 chips stacked on top of each other, and connected with a silicon interposer to the FPGA or GPU. It's still actually DDR technology. Those are DDR chips, but because it's all happening on a piece of silicon instead of a circuit board, you can use higher clock frequencies and wider buses. You get a lot more bandwidth. It helps both GPUs and FPGAs. Still similar of GPUs tend to put more stacks of HBM because they're just willing to put more cost into memory bandwidth. But technologically, FPGAs can do the same thing. FPGAs have a lot more network and I/O bandwidth, and I think you've already gotten the answer of why, right? Like it's mostly driven by just the applications they've targeted. And the compute model, right? You're right that the GPU also is kind of built as a whole pile of traditionally floating point engines that can just walk through memory. Yeah, so this paper is always, many years is kind of a controversial paper, right? Because peak analysis is dangerous, but I think there's some value here because you can take these numbers and say, if I'm doing a ton of floating point computation on a really big data set that's going to have to go in main memory, it's going to be really hard to beat a GPU, right? Maybe impossible because that's what it's built to do. So these peaks can kind of tell you which kind of devices might you want to go look at and give you a course partitioning of the space. Okay, so yeah, so let's go beyond peak performance now. I want to talk a little bit about programming models and some analysis of their efficiency. So this is the second paper that was on the reading list, and I think people answered before. A fair number of you, I think, have read this one. How many people read this paper? This is on Vespa, yeah. And actually, this is not on Vespa yet. Sorry, I will get to Vespa. This is another one by Rose. So it's basically, this actually has one of the same authors, which is what confused me. Okay, so we're going to get to Vespa in a minute, but this is another paper you were not assigned. Okay, so this one is trying to quantify, but I will get to Vespa, I promise, okay? So I keep like, this is like a build-up, right? I keep saying I'm going to talk about Vespa. So if you really like that paper, you're like, what is going on? Never talks about it. Okay, this is a paper by Professor Jonathan Rose, who's a professor here, and his grad student Ian Kwan, where they set out to measure what's the programmability cost of FPGAs. I told you there's obviously a big cost to using lookup tables instead of gates, using pass transistors, connecting fixed wires instead of making exact wiring you need. But how big is that cost of programmable logic versus ASIC gates? And this paper set out to analyze it. And so it's big, right? So they took a bunch of logic designs. So these circuits are all logic, no hard blocks, no RAMs, no DSPs. They're pretty small too. They ran them through, it's in this flow chart, so the details don't matter too much, but basically they ran them through Quartus, and they targeted a device where the area of the logic blocks is known, okay? And that area includes the programmable routing that comes along with them. So from the Quartus results, they could compute how much area on the FPGA is being used. And then they ran the same circuits through an ASIC flow targeting a similar process technology and said how big is the area report from the ASIC tool. And the gap they got varied some, but it was big, an average of 35 times. So, which sounds pretty bad, right? Do you have any concerns about this? So they're small designs, they don't have any RAM, they don't have any DSP. So what do you think? Is that, yeah?
I mean, most designs, DSPs are a huge reduction because you can put a lot of stuff. That's why we have the hardened blocks. Same for RAM, especially, almost all designs have memories, and those memories are not going to be implemented in soft logic.
Yeah, so I think this is a valid result, but it's pessimistic because most designs have DSPs and RAMs. And the worst overhead for FPGA programmability is in the logic and the routing, because it's the most different from an ASIC. When you start talking about a DSP block, it's more similar to the gates in an ASIC. It's not exactly the same because it still has some configurability, and it might be, maybe you needed a 16-bit multiply, but all that's on the chip is 18. You got to use an 18-bit, it's bigger, but it's not as big a gap, okay? So the logic only is going to hurt. The fact that these are small, do you think that makes a difference or not? These basically were about 1,000 LUTs for most of these designs. Somewhat even less than that. So I think the range of design sizes is like the hundreds to maybe 1,000 or 2,000 LUTs. Do you think that makes any difference? So I'd say it does. The reason is for an ASIC, if you have a really small design like that, it's going to fit, all the routing is going to fit over top of the gates, right? You won't run out of metal. As you get into larger designs in ASICs nowadays, usually you are limited by the metal, not by the gate area. So this is difficult to predict, right? It's different for different designs. But friends who design ASICs tell me their rule of thumb is that maybe you can, assume like you're going to fit 60%, right? Like you can pack it to maybe 60, 65% is a reasonable rule of thumb. You need the rest of the area for essentially some metal, putting in some buffers to keep your metal fast, keep your signals quick as the chip gets bigger and so on. That wouldn't really happen with such a small design. You just don't have as much metal. You don't have any long routes because the design is small. Now the FPGA this is actually I can't remember actually the device, but I think it was like Stratix 3. This device was architected for several 100,000 lookup tables, meaning that the programmable routing channels are designed to be wide enough to have enough metal that designs of that size will successfully route. So the logic block is somewhat bigger than it would need to be for these designs. This isn't going to be like a factor of 10 or something, but this could be like a factor of 2 that's kind of buried in this data that the ASIC results are kind of optimistic because you've got a small design, and the FPGA, you're taking a chip that was architected for much bigger things, but not using that. Does that make sense? But even if you say, okay, maybe it's optimistic or pessimistic by a factor of 2, maybe that gets you down to 20x, but it's still a big number. And I think 20x is probably a little closer. The bigger problem, though, is, or not problem, thing to consider, is that hard blocks are not, they're not a minor thing, right? So FPGAs include a lot of RAM blocks, a lot of multipliers, and a lot of I/O that is a big part of their value proposition. So we shouldn't neglect that, and Dr. Rose tried to take that into consideration, okay? So for the circuits that they used, if they include all these hard blocks, it did cut the area ratio, but only from 35 to 20. However, the circuits they used are kind of old and small, so only a few of them had multipliers, and only a very few, 3 of them, had logic, multipliers, and memory. And the gaps did get smaller as they had these. The number of designs, how many designs do you think that are 500,000 lookup tables and so on have no memory? Like 0, right? Like what are you doing that you basically have like some computation that needs no data and has no storage but is gigantic? Like it is very difficult to think of what that computation would be. So this is a sign that these designs are probably a bit too small and simple. So the hard blocks are reducing the gap some, but probably their designs are not actually very representative, right? FPGAs have a lot of these hard blocks, their designs aren't using them much. So they did another analysis on this. And when they did this analysis, I was at Altera. I remember when they presented at a conference, presented at an FPGA conference, the audience had many hostile questions, including me. So this was one of my suggestions. If your benchmarks are not actually very good, you should do another analysis where you assume that people design to the chip and they try to use the resources that are there, which they can't always do. So this is kind of now an optimistic assumption. But they basically said, okay, let's not use a benchmark now. Let's just say we're going to use everything on the chip, okay? Not the I/Os. We don't quite know what to do with those. But let's say we're going to use all the RAM blocks, all the logic blocks, all the DSP blocks. It's kind of the best case for the FPGA now. It used everything, right? There was no wastage. So that's optimistic. If they did that, the gap got much smaller, but it was still significant, right? So 4.3x. So no matter how you slice it, FPGA programmability is expensive. Now this is still the core, okay? So it doesn't include the I/Os. Now the I/Os are a significant part of an FPGA. So the last time I analyzed this, I was part of a panel where I looked up the data for one generation, I think Stratix 4 of FPGAs. The I/Os were between 20% for a big chip and 50% for a small chip of the total area. So if you include I/Os, this would drop more, because actually a big part of an FPGA's value add is I/Os, especially for the smaller ones. But this is a reasonable number for kind of the core that's doing the computation. Okay, what about the delay gap? Okay, so for the logic-only circuits, they found a significant delay gap, 3.4x. So the ASIC was also significantly faster. Do you think this is going to change when we go look at the designs that have hard blocks? So the area changed quite a bit when we brought in hard blocks. Do you think the ratio for delay will change too or not? What do you think, Isidore?
I think it depends really on what computations are limiting for the design.
So they didn't re-optimize any of these circuits. So they just, they're black box circuits. They got a bunch of circuits. So what do you think they'll get on average? So you're right, but I'm going to push you to predict. Much more than 3.4, much less than 3.4, around the same.
I think it'll be around the same. I don't think they'll get huge.
What do you guys think? Are you with Isidore? People are nodding. Yeah, so that's a good guess. So basically, the hard blocks don't really change the speed much. We'll bring in their limited number of designs that have multipliers, about the same average. RAMs, maybe a little lower. And this makes sense. Area, you're adding everything up. Okay, so you get a big win on some hard blocks. That goes into your area budget. Your delay is limited by the slowest path in the design. And especially for these designs where they haven't really optimized them for any particular thing, they're just designs they got, right? They're not changing the logic, they're not repipelining them. what will normally happen is if you have hard multiplier blocks, it's just not going to be your critical path. They'll be somewhere else. So you don't get the same kind of changes in relative delay. It's just going to be the logic that determines that. But area, those hard blocks do make a difference. We found this industrially too. When we did the architecture studies that resulted in putting DSP blocks into Stratix, the first Altera chip that had it, we found something similar. For multiplier intensive designs, they reduced area by 5 to 10x, depending on exactly what kind of multiplier size we were using, so it was big. For speed, it wasn't much. And it was because we weren't redesigning the circuit. If we redesigned the circuit and repipelined it, maybe we would have gotten something. But without redesigning the application, your critical path just moves. And the next critical path is probably not that much shorter than the ones through the multiplier, so you don't get a gain. So summarizing that, so area gaps vary a lot. Okay, so if we said we're going to use kind of everything in the core, it was about 4x. If we said it was logic only in small designs, then it was about 35. I think most cases you're going to be closer to the 4 than the 35, but it's a big number no matter what. I already told you about this, a couple of the reasons why I thought that was optimistic, because of white space. Speed was a bit more consistent, around 3x. Okay, so area delay product is essentially the opposite of efficiency, right? If I want to get more throughput out of a device, I can clock it faster, or I can make more replications of some computation. One of those is the inverse of delay, one of them is the inverse of area. So area delay is like the inverse of throughput. I would like it to be small. So if I take the area delay product of an ASIC versus an FPGA, it's big, right? I get 12x to 60x, depending on kind of the assumptions I make. One of my PhD students, Andrew Boutros, did a more recent study on this, where he took entire CNN accelerators, so definitely more modern, much larger designs, had lots of multipliers, lots of logic, lots of RAM. And the results he got was that the FPGA gap, area gap was about 8x, and the delay gap was about 4x. So, kind of fit in this range, right? So these numbers look fairly solid. Okay, so so these are big numbers. So you could go, wait a sec, what can I transfer to the can I transfer to the ASIC course, right? So it's too late. So we've got to find some way to be more optimistic. So I guess one caveat on this. This is an ASIC and an FPGA in the same process generation. I talked about how expensive it is to make an ASIC. Okay, so if you're NVIDIA, you are going to make an ASIC. Okay, so you're going to make it in the most advanced process generation you possibly can. So, these are the kind of numbers you're going to get, and you're not going to put your new GPU on an ASIC, on an FPGA. For most companies, they can't afford the latest ASIC, right? So the latest FPGAs are in 7 nanometer technologies. Most ASICs are not done at 7 nanometers. The absolute most cutting edge ones are done at 7, even at 5, but that's a few very high volume. So the average ASIC lags an FPGA significantly in process technology, and it's because their volume is smaller. It takes longer to design. You can't afford the same NREs. There's a bunch of good reasons for that. It's hard to get data on this. I did a bunch of web searches trying to see if I could find a DataQuest report. When I was at Altera, we got lots of data on this, okay? And the average was 3 generations. So I don't have a more recent number, but the average, gap was, if the FPGA would be at 7 nanometers, 3 generations would be 10, 14, 22. Okay, so you'd be comparing a 7 nanometer FPGA to a 22 nanometer ASIC. And this is a rule of thumb. I can't, tell you that that's what's always going to happen, but historically that's what the gap was. Okay, what does it mean to be 3 generations behind? That's a loss of 8x in density and about maybe 1.5x, maybe 2x in speed. So it's 12x area delay if I multiply those together. And that goes a long way towards closing this gap. So that's often the efficiency comparison that you are actually making, right? Like that's what you can afford. Or maybe you can't afford an ASIC at all, in which case it doesn't matter. So it means that even three generations behind, that ASIC may in fact be no more efficient, or maybe if I take the most optimistic numbers for the ASIC, 8x more efficient. But probably I'm not going to get those ones. Okay, but that's not the whole story either. Okay, so we also have to think about the programming model. Because in all the studies I just showed you, both the Rose study and the study by Boutros, there's no programmability in the circuits. Like when they put these circuits in an ASIC, if this circuit was like a big XOR tree and then a multiplied, that's all it does, okay? The CNN accelerators that Andrew Boutros put in an FPGA versus an ASIC, he hardwired everything. These are RTL circuits, so that ASIC would do one exact neural network. That's it, right? It would do like VGG16 or it would do ResNet 50, nothing else, right? At a certain precision. You want to change any single thing, you throw that ASIC away, okay? So it is a real comparison of this hardware versus that hardware, but you would probably never make that ASIC because that ASIC is so inflexible that it doesn't make economic sense, right? There are very few applications that you're that sure of they're not going to change. So what that means is that when you put something in an ASIC, you normally have to put programmability back in somehow. Okay? One way you put programmability back in is you actually don't do it all with streaming hardware. You do a lot of it, or maybe all of it, with processors because you need some of that programmability back in. So finally, we get to the Vespa paper, the long awaited. So this paper tries to answer what is the cost of different programming models. And they're comparing, so they want the same implementation substrate, right? They don't want any ASIC versus FPGA polluting this calculation. So they're comparing a processor that's a soft processor built in an FPGA versus hardware, basically streaming hardware built on that same FPGA. And they build a few different processors because that's what their infrastructure can do. So they build a scalar processor. So scalar means no SIMD, right? One instruction means take two operands, do something on that, make one output. And they found that it's 432 times slower than the streaming hardware and 6.7 times larger, which if you multiply those together to get the inverse of throughput, it's big. It's like a 2900x difference. Now, if you've got a significant parallelism in your application, you're trying to optimize for throughput, you probably wouldn't build a scalar processor, right? A vector processor with SIMD instructions will typically be more efficient because you're amortizing your instruction fetch and decode. So they also did that. They looked at a variety of vector processors, and vector processor again just means SIMD, right? They're synonyms. This cut the speed a lot, right? Because now one instruction can compute many pieces of data, so it's only 25 times slower. It got bigger because the SIMD means they've got more functional units, so it's 36 times larger than the hardware version. But if you multiply those together, it's still significantly better, right? Like their area delay is now 900 times worse than the hardware. So they've closed the gap by more than a factor of 3. And they investigated what was the best SIMD, and they found for these applications it was 8-way. If they went wider than that, it didn't pay for the area anymore. Okay, so is everybody with me so far? You understand the study they did? This chart in prior years has often confused people. I've tried to tune it up, but tell me if this is confusing. Okay, so this is trying to put together these two competing things. If we use an FPGA, we can now use a more inflexible programming model because the low-level hardware can be reprogrammed. If we use an ASIC, we're probably going to have to use a more programmable compute model because of the fact that we can't change our wiring and our gates. Okay, so the most efficient way we could build something is going to be an ASIC. And if it's a repetitive calculation, which is what these applications were, directly implementing that in hardware, so say streaming hardware, is going to be the most efficient thing. And I'm going to define that to have an area of 1, a delay of 1, and 1 times 1 means area delay of 1. Okay, so that's my baseline. Okay, but now I can't afford that ASIC, or I think it's crazy to basically commit to this exact piece of hardware that does exactly one thing. So I'm not going to do that. Instead, I'm going to say I'll take that same Verilog or VHDL, that same streaming hardware, but I'll put it in an FPGA. And from all the calculations we just did, we saw that's going to be quite a bit bigger, and it's going to get an area delay product that is somewhere in the 12x to 60x worse range. Okay, so a pretty broad range and quite a bit worse. But now I go, okay, well, I can't really make an ASIC that does just one thing. right? There are more computations I need, more variability in my end market. So I'm gonna make an ASIC that has a scalar processor in it, plus some custom IOs and whatever. And we just got the number from Vespa for that. So that cost of that in area and delay is high. So that's 2,900 times worse. I also know that that's not the smartest thing to do, so I optimize my processor and make a vector one, build that again in an ASIC out of gates and wires. It's 900x. The two things here that probably make sense, okay, from an economic perspective, are I can make an ASIC that has a vector processor in it, or I can make an FPGA that has streaming hardware. Because both those things I can reprogram to adapt. Does that make sense? Whereas this one will be lovely, but I can't actually adapt it. So I think that one is just not really viable. So I cross that one out. These are the two ones that are left that look interesting. And if I just divide those by each other, I wind up with, what does that streaming hardware in the FPGA look like compared to a vector processor built out of actual gates and wires? And the streaming, in these particular applications, the streaming hardware comes out quite well. It's faster, it's same area to somewhat bigger, and that gives me a better area delay. Yeah?
Just a quick question. So taking the number from the paper, comparing the vector versus the vector versus the hardware. In the paper, those were both on an FPGA.
Yeah.
If you put the vector and the hardware on an ASIC, you're likely to get very different numbers because you're going to build a different vector processor. You're going to want to put bigger caches, and you're going to want to optimize it more in ASIC than you would in hardware and on the FPGA.
It's a good question. I actually don't think the numbers will be that different because they're all ratios. Do you know what I mean? Now you're right, they won't necessarily be exactly the same. I think that what you want to do is make sure you're comparing on the same substrate, right? Like, so either they're both going into an FPGA or they're both going to an ASIC. And you're right, maybe the ratios also change. I'm postulating those ratios are approximately constant. Does that make sense? But that's essentially postulating, right? Like, I can't prove that. The other thing I would say is, do not take this table and say, I guarantee an FPGA is 9 times more efficient than a vector processor, right? There's a whole pile of caveats on this of, what were the applications and so on. They didn't get the same answer for all these applications, and the applications that they benchmarked in the Vespa paper may not be the same ones you have. So it's not a statement of an FPGA is always the best answer. It's, I guess what I'm trying to highlight here is roughly what is the cost of FPGA programmability, and it's quite big, but at the same time, the cost of a processor's programmability is also very big. Yeah, does that make sense? So you have a big hardware cost for the programmability in an FPGA, and part of this course when we get into architecture is what are ways to make that somewhat less, but it's not going to zero. But it does enable this much more efficient programming model. The net result is usually you can beat a processor if there's enough parallelism, although that's not always the case. But there's a big range of results too. So the bit widths, what operations you're doing, the amount of parallelism, the memory access, all going to affect this. So it's not going to be just one number, even though I'm boiling it down to ranges. But I'm also acknowledging if you start to do this application by application, it's not going to be one number. Does that make sense?
Also, with their vector processor, weren't they hand-tuning like the number of lanes and all of that for the particular application? Whereas if you were to do it in an ASIC, you would just pick one that's big enough for the biggest application.
Yeah, I think I took the numbers from when they basically did actually, I think they were tuning it. You're right. I think I took these numbers from the ones that were actually tuned per application, which is probably fair. This gets into like, well, how wide is your application space? If you know your application space is in this domain, you probably can tune the number of vector lanes and have some confidence that it's still roughly right. If you have almost no idea, then you can't. You're right. You have to kind of just pick one and stick with it. Does that make sense? Okay, so questions, caveats. So I want to put caveats on this. So the reason I did this was to get, people wonder about this all the time. Like, how efficient is an FPGA? How efficient is a processor? And I can't give you perfect numbers on it, but I think this is the right way to think about it for a high level analysis at least. But now I also want to think about caveats, okay? Because I also don't want you to, take these numbers as gospel and just start applying them madly, because that would be bad. Alex, did you have a comment?
I just had a comment. I love the Vespa paper. I actually disagree with how they collected the results between the
Oh, okay.
They instantiated a scalar processor, which they called like a certain architecture. Then they created a vector processor, which was the same exact architecture with a vector coprocessor.
Mm.
So obviously that would perform better. But also they hand tuned their test cases with they hand wrote in assembly the vectorization. Which I also thought was not very fair because the scalar one they weren't doing any hand tuning. And the hardware one they kind of had a whole section where they kind of say like we didn't unroll something, did unroll something else.
Yeah.
So I was a little confused by that. I was wondering what you thought about that.
I have to go back and read the paper again to give really detailed ones. I'd say compilers are getting better at vectorizing. The reason that they would have handwritten the vectorization code is that the compiler wouldn't have done a good job, right? And that was definitely the case. I mean, in assignment 2, you're going to see you can actually turn on auto vectorization versus not, and compare it to hand vectorized code. You don't actually have to write the code. We give it to you because I'm not trying to make this a secret compilers course. So don't get scared if you're like, wait a sec, has it learned all that stuff? No, we just want you to see the impact. But historically, like until a few years ago, I would say that most compilers were fairly bad at auto vectorizing code. So they didn't use SIMD very well. NVIDIA's tools, right, CUDA, because it embedded it right in the programming model, did, right? So that was one of the big advantages where they've gotten better, okay? But at the time that they were writing this, I would say if they didn't handwrite the assembly for the vector units, they probably just wouldn't have used it much. They would have gotten an answer saying the scalar processor is better than the vector because we don't use the vector units. That's not a super useful answer. So they went, we're going to go in, we're going to handwrite the code. It's more effort, but we're going to get an answer we think is closer to what can be done. In any study like this, where you take a bunch of benchmarks and try to implement it in multiple ways, you always have this like, how much effort do you put in? I think the best you can do is put in a reasonable amount of effort and try to make it consistent. Does that make sense? Because you could clearly point at any one of these things. If you can point at each of the architectures and say you could make that a bit better, then that's probably reasonably fair. If you point at one and say you could make this way better, and this one you spent a year and a half on, that's bad. It seemed to me that they spent a reasonable effort on both. Does that make sense? So I guess I've told you some caveats. Any other caveats or questions? Yeah.
One thing I've noticed was they're comparing two streams. Like they're comparing just like a pure scalar processor versus like complete in hardware.
Yeah.
And they're not comparing to other, perhaps like other intermediate. The main argument they made for the vector processor is that it's like easier to program than doing pure hardware, and it's not as much work as, like it's not as much work doing pure hardware, and it's easier for like roughly the same ease of programming you would get with the scalar processor. But there's other things they could have done, like, for instance, scalar processor with custom, hardware extensions on the side,
Yeah.
as an example, or VLIW, or
Yeah.
other architectures that probably would have been on the same order of improvement and wouldn't have been as difficult to program as a pure streaming hardware.
Yeah, and that makes perfect sense. So we basically got ASIC and a vector processor as an example of something that uses gates and wires but is still highly programmable. And you could take other things, you're right, where you say, look, I need some processor, but maybe I've identified 3 key coprocessors. I build all 3 of them. That costs me some area, but still it's more efficient than doing everything in the vector processor. And you're right, ASICs will try to do that, right? So that's the cleverness of trying to mix hardware. Like, where do I need the program building and where do I not? And that's where you could get a very efficient ASIC. One of the things I like about this chart, because I made it, is that it does highlight, though, that you often, basically in the literature, you'll see people just take the Quan and Rose paper, and they'll actually take the first number. They take 35x, and they say ASICs are 35x more efficient than FPGAs, which that number is probably wrong to begin with, right? Real number is probably more like the Boutros number, 8x. But that 8x is for something with no programmability, which is usually not manufacturable. This says if you need a lot of programmability, you make like a vector processor. It's actually worse than doing an FPGA, and I believe that result for most applications. But it's also misleading in the sense of, if I know more about my application, I don't need to try to do everything in the vector processor, right? I could make some coprocessors, put some in hardware, and I'm going to wind up somewhere in the middle, okay? So anyway, that's why design is a difficult thing. So yeah, so caveats. So I think we just identified some, right? There's a lot of hybrid solutions, which in fact are often the most interesting ones. If you were doing an ASIC, that's what you should try to do. Anything else? Yeah.
I was thinking about that one, when they were, the
they said that just having a bigger memory or register file with the vector processor, like with the add-on of the vector processor, and not really vectorizing it, just having one lane, that itself reduced the, I think from 400 went down
Mm.
to that. So, I mean, they didn't really vectorize it, and just having a bigger memory was enough
Right.
to give you like 200 times more, performance. So that's
Probably about 200 times. I think you mean, do you mean
yeah,
like
so it
2
went
times?
from, like the cost went, yeah, so like cost went from 400 to 100,
Yeah.
200x.
Yeah, so I guess you're pointing out that like you can optimize these processes in other ways, like what's your
Yeah.
register file size, et cetera,
Yeah.
right? Any other caveats? I think it's a good point. Any other, I mean, there's a big one that I would add here. So in any study like this, you need to really look at the benchmarks, right? And because you're not going to get just one answer. I mean, we saw that for the FPGA versus ASIC, that like how much you use the hard blocks is going to change things quite a bit. It's even more important for this processor versus hardware comparison. So the benchmarks that they used had operand sizes of 1-bit, 8-bit, 16, 16, 32, and 32, and they're all integer. So they do have a range. Their numbers are going to be pretty different, right? 1-bit is really good for hardware, right? All your units are really small, and most of your processor data path is wasted. So when, I think it was the Viterbi decoder. So that's going to produce huge gains for the hardware implementations. As you get up here, your data path is bigger, so the overhead of register files and instruction fetch is larger, but it won't be quite as catastrophic. So operand size is going to matter, right? And the more you go this way, probably the more beneficial hardware implementations are. The fact that they're integers, if you had to do this in floating point, your data path gets bigger, okay? So that also helps, basically helps amortize the inefficiency of instruction, decode, and so on. So the hardware versus processor gap would shrink some as you went to larger operands or floating point. You also could, I mean, you could say if I know I'm doing all 16-bit, maybe I should make a 16-bit processor. Could save me some, although it doesn't really help me much with instructions and stuff. So it's going to make me somewhat more efficient, but not as much more efficient as the hardware can get. I think we already talked about. So the scalar processor, for these kind of computations with a lot of parallelism in it, you're not really going to use a scalar processor. So the vector processor is really the baseline that you would want to compare to that's highly programmable. And yeah, so the other thing I should say is all of these designs were chosen to be reasonable targets for hardware, right? They're kind of repetitive. There's a fair amount of parallelism in them. And that makes sense for their study, right? Because choosing something that is all control flow is pretty obvious that is not a good target for hardware. So they focused on things that are a good target. But that's something to bear in mind too. There are classes of applications out there that you would get a different answer, right? They're focused on getting a lot of data from some big data set and memory and making conditional decisions. A processor is probably going to do quite well on those. And that's all I had for today. So I think I went over time by 7 minutes last week, but you get it back this week. So